All right, we'll make a start. Thanks for coming along the late Friday afternoon. Good, you've all stuck around, excellent. We're going to talk about lowering, which is a word that if you say it enough, it loses all its meaning. But there's a pretty good chance that some of you won't know what it means anyway. So let's talk about it. What is lowering? So imagine you're writing a compiler, C# compiler, and your job is to write a method that takes a foreach loop, the code for one, and outputs some IL, right? Compiles it. This is not how a compiler is written, but let's pretend that we have one method called compile foreach. Now, IL is, I'm going to say reasonably complicated because I don't understand it and therefore it's magic. But C#, I do understand. So in my mind, I'm thinking, well, rather than write this foreach to IL method, I know how to rewrite a foreach loop as a for loop. So I will write that, and now I can worry about writing a for loop to IL method. I kill two birds with one stone. Great, do less work. And of course, then you keep thinking like, well, a for loop is just a while loop if you reorder bits. And if you really want to go crazy, a while loop, well, you could just write that using goto statements. And now, if I convert all this C# and stay in a language that I like and understand, I can write one method, compile that to IL, and I get sort of 4 things for the price of 1, right? If we do go all the way to IL with this little code snippet, and this is the only IL in the talk, and I barely understand it, so don't worry, but this is what essentially all of those bits of code look like, kind of. And there's familiar things here. We have get item, so we're pulling an item out of the loop. We have get count. We have to do that to compare the count at the end. And at the end here, we have the bacon, lettuce, and tomato sandwich, which is not what that means, but I told you I didn't know IL. That actually means branch if less than. That is the thing at the end that says we've got a count from our loop. We've got a value in our indexer. If there's still more to go, let's loop back around. It does a branch. And if you have any experience with IL or with assembly, because they're very similar, branching is kind of all it can do, right? There is no blocks in IL. You can't have, it doesn't have loop constructs. It's all just branching, which kind of means it's all just gotos. So if you think about having to implement a for each loop, if you've got to implement it in IL and you therefore will have to use gotos, maybe it is easier to go all the way through to goto statements in C# before you get there. That's not actually what happens, but anyway. So lowering is going through these lower level constructs, but in the language that, in the same language, in the language that you're compiling. So there you go. Eric Lippert has that little sentence. I don't actually know if lowering is a sort of technically correct term, but it seems to be what everyone calls it, so that's what I called it. But basically the idea is you stay in the same language, you just go through lower level features. If you go from a high level language to a low level language, well, that's called compiling, so it doesn't make sense to call it that. The thing is we all use lowering every day, probably. And one of the most sort of commonly known one is with link queries. So I'm hoping that most of the people in the room who've used a link query know you can basically write this 2 ways. We can write with query syntax, or we can write with the method syntax. And it's pretty prevalent that these 2 things coexist. There's reasons for why you might want one or the other. Even in Visual Studio, there's refactoring that offers you to convert from one to the other and back again. The query syntax gets lowered by the compiler into the method syntax. Rather than compiling both of these to IL, they simply convert from one form of C# to the other and compile that. And in fact, these methods are extension methods. If you've ever written an extension method, you know that it's just a fancy way of writing a static method. So you can go even further and say that, well, you could lower that method form of a link query into normal static method calls. So all of this stuff is happening all the time in C#. Something as simple as defining a variable. This has to be lowered, right? There is no IL concept for var. There's not even a .NET concept of var. Var is a C# thing. So the C# compiler, in order to produce a .NET DLL, has to do something with it that .NET understands. So the compiler essentially rewrites your code or pretends that you wrote string. So we're all using this all the time. It's also used to optimize, or I may optimize, but improve your code. There's minor little optimizations the compiler makes. So if you wrote this code and you had 2 string literals, this could be compiled down to call the add operator on a string, pass in the left-hand side and the right-hand side, and that'll combine these strings at runtime. But the compiler is smart enough to know that it can do the same job at compile time. So to save time, if you write that code, you're essentially compiling that code. Compiler just munges them together. And so there's lots of these little optimizations. If we have 3 parts to our string, now if these were all string constants, the same thing holds true as was on the previous slide. But if these are parameters or variables or fields or anything else, the compiler can't do that at compile time, obviously. That has to be done at runtime. So logically, with the plus operator, you would have to do this, right? Operators in C# have a left-hand side and a right-hand side. They only have 2 parameters. So you would have to have a temporary variable, add part 1 and part 2 together, then add part 3 to our temporary variable. The compiler does this all the time to allow you to write easy code without defining these temporary variables yourself. But of course, if it did that, that temporary variable is now something the garbage collector has to go and clean up, right? That's an allocation that you maybe didn't intend. So to improve this, if you write this top bit of code, what the compiler actually does is lowers it to string.concat, which pre-allocates 1 string, copies the bits in, and away we go. So there's all these really small little optimizations that you're getting the benefit of all the time. Even something as simple as this, again, that M is not a .NET thing, that's a C# thing. So that is calling a constructor of system.decimal. It's not very exciting, but that's what's happening. So why do we care? Well, there's kind of 2 reasons. Number 1 is understanding about the performance of your code. That's the reason that if you want to go home and tell your boss on Monday, that's the one to stick with. I write code like this all the time because this is what my brain says to do, or possibly just my fingers do it without my brain even catching up. Concatenating strings, that's just what I do. Some people like string format, some people like this way, I go this way. And in C#6, string interpolation, or interpolated strings came out, and everyone in the code base I was working on went and changed them all to this, which is cool. This is very readable. I like the little colouring you get in Visual Studio with the count thing, it's cool. But if you know what the compiler does with your code, when this came out, every time someone changed the top line there to that second form, it's a readability improvement, but I saw a potential performance degradation because string interpolation lowers to string.format. And string.format is, generally speaking, slower than string concatenation. Now, it's slower because it does more and it does good stuff. It does like culture-sensitive things. So in this example with count here, I'd actually argue that top line is probably wrong and it probably should have been string format because if count was more than 1,000, you might want the little 1,000 separator. And of course, whether that's a comma, like here, right? 1,000. In Europe, it would be a dot. String.format is aware of that. Maybe I shouldn't have mentioned Europe today, but never mind. So this is a potential performance regression, let's say, right? This is probably unlikely to break your app and make it crumble, but you never know. It's something to be aware of. Now, the good thing is that since C#6 came out, I think like maybe 6 months afterwards, there was a contribution from the community that improved string interpolation, so it will also lower to string.concat if it can. So there's kind of less reasons to worry now. Essentially, well, you kind of don't have to worry because if it's going to use the string format call, there's an argument it always should have been. But so performance is kind of not really performance either, just understanding performance is kind of the main reason. But the other reason that I like to know is because I like to know. I'm interested in this sort of thing. And it's funny because I think I've seen this quote at least 3 times this week because I think this is a very common thing that all developers like to understand how things work. And so that's why I like to know. So back to our for each loop, though. This is a for each loop. It's not very exciting for int m in values. Now, the body of the loop there I've colored in green because I want you to ignore it. It's like a comment, right? From the compiler's point of view, we assume that it doesn't know what's inside the loop. Obviously, it does because it has to compile it. But by extension, even if it knew that console.writeLine's there, it doesn't know what console.writeLine does. So that kind of doesn't factor in. But needless to say, that's the body. It's green so you can see where it goes. So what does the compiler do when we get a for each loop? So we can't talk about for each without talking about IEnumerable and IEnumerable of t. They're relatively simple interfaces. IEnumerable has one method which returns an enumerator. It's called getEnumerator. And an enumerator has a current, which is the current thing we're pointing at. It has a movenext, which returns whether the move worked, not whether there is more, but whether we did move. And it has a reset method, which no one has ever called. And then IEnumerable of t and IEnumerator of t is the same thing, but we redefine a couple of things in terms of t. I am sure this is one of these examples where if generics existed from C#1, this would look a lot cleaner, because this is kind of, but anyway. But so for each works on IEnumerables, right? Everyone knows that. But it kind of doesn't. Let's write a for each loop. So I will write this, no. Thank you. Right. I'll write a for each loop. Now, obviously, this doesn't compile, but I'm going to have a thing. That's what I want. And I'm going to create a class called myThing. So this doesn't compile, as you would expect. And if we hover over this, you can't read it because Visual Studio doesn't zoom tooltips. But that says blah, 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 getEnumerator. But it doesn't say you don't implement IEnumerable. It just says you don't have a getEnumerator method. And in fact, if we write one, let's call this one myEnumerator. GetEnumerator. I love that it suggests the name. It's so clever. You know what? I don't even actually need to do anything here. If I do this and then create that class, ooh. So this still doesn't compile, but this error message you can't see is slightly different. This now says you don't have a current and you don't have a movenext. If I give this a current, I can make it an object, doesn't really matter. And we give it a movenext, which can always be false. And this now compiles. So there's no IEnumerables, there's no IEnumerators, there's nothing. For each is pattern-based, which is the boring way of saying it's duck-typed, meaning if it looks like a duck and sounds like a duck and walks like a duck, and it's probably a duck. So this is interesting thing number one about for each loops. Yes. It's my first time using virtual desktops. It's very exciting that it worked. So all this stuff with IEnumerable, see, I didn't even need reset because no one ever calls reset. You actually don't, we don't need that. So the compiler doesn't use it either. So what does it look like? The first thing the compiler has to do when we have a for each loop is we have to introduce a scope. So it's very subtle, but there are braces there. And that's simply because our int m in our loop, we can't use that anywhere else. So we have to contain it. It's easy enough. So we call getEnumerator on our values, and we get it back. There's no casts, there's no checking if it's IEnumerable, etc., all those things. We just call getEnumerator. You can kind of think of this as long as that line of code compiles, then everything is fine. It's not technically true because extension methods don't work, but that's a choice that they made. There's no great technical reason why not, other than presumably it'll break things. But so we get an enumerator, and it's a var, because we don't know what it is, but we don't care, right? As long as it has the right methods. We have a try finally, because error correction is good. And then we declare our loop variable, and then while we can move, we move. So that's about it. For each loop's lower to a while loop. 15 minutes in, good talk, yeah. Let's go a bit further. Haven't used the current property yet, so we get our current value into our loop variable, and then we have our body, which we're all going to ignore, right? Everyone happy? Who's itching to raise their hand and tell me? Thank you, John. Why are there two casts, he says. So this is where, for me, it gets interesting, because knowing what a for each loop does, it's a little bit interesting. I like knowing what the compiler does, so fine. But when you get up to something like, why are there two casts? That's when I'm like, okay, I have to find this out now. This is now just going to bug me if I don't know. So let us have an aside. This is a loop. Well, pretend that two different developers wrote this code in the box here. Developer A wrote an object array and put some ints into it and then called a method that took an object array. Fine. Developer B wrote a method that takes an object array and pulled some ints out of it. So this looks fine, and if you read that in English, it says for each int in my array, it kind of sounds like, oh, that's going to go through my array, find the ints, pull them out and do something with them. But if we look at the code on the left, which is what the compiler actually outputs, that's not true, right? That's not what's happening. There's no looking to check if there's ints, there's just casts. So if you get the types in this wrong, you will get an invalid cast exception. Maybe some of you have seen this at runtime, it does happen. And if you look at the code on the right and you think, I mean, why would you get an invalid cast exception? There's no casts there. Well, now you know, the compiler puts 2 in. So there are 2 casts going on here. We have a cast from int to object to go into the array, and we have a cast from object to int to come out of the array. But it kind of doesn't explain it for me, so I'm going to change the example a little bit, but due to space constraints, it gets a bit confusing. So bear with me. Hopefully you can follow along. If we change our array to a person array, and we put employees into it, and then we, instead of pulling out ints or persons, we pull out customers in the second bit, the 2 arrays now become required. So don't forget, this is developer A and B, they've never talked to each other, they haven't met, right? Developer A's job, he's putting employees into something that wants people, so he has to provide some kind of way for that to work. It could be through inheritance that it works, it could be through an implicit cast operator or an explicit cast operator, doesn't matter. Somehow that translation from employee to person has to work. And then developer B, they're writing something that translates from person to customer, and so they have to write something that makes that work. But they're each within their own domains, right? So when this code runs, current will be an employee. The first time it gets cast, it will be cast to a person, and that translation is supplied by developer A. And then the second time it gets cast, it will be cast to a customer from a person, and that translation is supplied by developer B. So that all works. If we only had one cast, you'll be pulling out an employee, casting it to customer. That could potentially blow up, but more importantly, from each developer's perspective, that is completely and utterly mysterious. Right? If you've written a method where you put employees into something that takes people and it throws up saying I expected customers, you have no idea why. You have no idea that he expected that. And same thing if you write a method that expects customers and you'll get given employees, you have no idea. These two developers might not even know the other class exists. So the 2 casts allow this sort of pipeline through from what we put in the array to what type of things the array can store to what type of things we're pulling out of the for each. I find that interesting because I know that I would never be smart enough to come up with that if I was designing a language, but after the fact I can look at it and go, oh yeah, I kind of see how that works. Anyway, and then we dispose things. And that's how for each works. Now the dispose has got a little bit of poetic license as well because inside the compiler it knows if you're idisposable and it'll just leave out that call if you're not, but this is a PowerPoint slide, so you get that. So that's a for each loop. Cool. If you go home or go back to work on Monday and you write a for each loop and you compile it and you look in ILSpy and you look at that DLL, don't try and show off to your workmates and say, I know what this is going to look like, because it won't look like this. Because this is a C#4 for each loop. A C#5 for each loop looks slightly different. Watch the M. In C#5, our int M declaration moved inside the while loop. That's it, that's all that happened. This solved so many Stack Overflow posts. It was ridiculous. And again, this is where this stuff is interesting. This is like historical interesting now. So what happened in C#5 that caused this? Well, that's actually a little bit of a false question. It's what happened in C#4 that caused them to then fix it in C#5. And, well, I won't spoil it yet. What happened in C#4 is link and lambdas, right? And it exposed I don't want to say bug, but there was an assumption in people's code, and it was possible from back in C#2 with anonymous delegates, but LINQ, made everyone start writing more lambda expressions. So it just got a lot more noise. But yeah, anyway, I won't spoil it. But to talk about what the problem is, we have to talk about closures, which means we have to talk about lambdas. So a lambda. In green there, or actually, well, in green is the body of a lambda. Technically, I guess the lambda includes the x bit. But anyway, so we're defining a lambda. It's an action. It takes in one parameter. Fine. And we're going to call it. Conceptually, this lowers to this, which is your action is a method pointer. We call the action, which ends up calling the method. Great. Realistically, this isn't how the compiler works, because having this method here on your class could potentially be a problem. Again, because it doesn't know what's in the body of the lambda, right? It doesn't know what console.writeLine does. It could be something that has to hold this instance of C in memory forever. So if this class is a Windows form with 100 controls and lots of event handlers that uses up lots and lots of RAM, whatever, and defining one little lambda is going to result in this being held in memory for the entire life of your application, that could be a bad thing. So the compiler can't really prove that this is going to happen or not going to happen. So all it does is it tries to generate code that will avoid it as much as it can, which just means in practice, it generates a little class to hold your method, so that even if something goes wrong in this class, this instance is held in memory, at least it knows it's generated the smallest class it can. There is one more step to this, which I'm not going to cover, because it doesn't apply as soon as you close over things, which is what we're talking about. But if you're interested, you can go and find out about that later. But so here's essentially how a lambda expression is lowered. We have a helper class that gets created. We point to the method on that helper class. Great. So what happens if we close over something? So closing over something means if we modify our lambda to refer to something from outside of it. So just to recap, this is our lambda. This is what it looks like when it's lowered. So if I add in a y here, so we're now writing out x plus y. We've defined y locally. So we're closing over y, right? The lambda is using something from outside itself. Our code on the right, obviously this now doesn't compile anymore, because where does y come from? So what happens is any local variable that you're closing over gets hoisted up to be a field on the helper class. So now this helper class now compiles again. We have a y. Every reference to the local in your method gets replaced with a reference to that field. So we create a class, we set something on a field, call a method, right? This is reasonably straightforward. If we change the value of y to fish, then all we do is set that field to fish. So from this example, it's relatively clear, hopefully, that this is going to print out hello fish, right? We're closing over y, not the value of y, but the variable itself. So we're always getting the latest version of it. When you write out code like this, it's reasonably expected. Once you bring loops into the equation, though, things just get a bit more hidden, and it sort of revealed some problems. Do let me know if this is like too whatever. This talk's kind of a bit of a roller coaster where it's like gets really complex and whatever and falls off a cliff at the end. If you start to feel ill, I won't be offended if you leave. Put a green card in so I know you were sick. So let's go back to our loop, and we've got to change our loop now to have lambdas in it. So instead of actually writing out what we want to do, we're going to assemble a list of things, which I would probably call tasks, but that keyword is taken. So our loop now is just going to add things to a list, but it adds lambdas, and it's capturing our m. So in C#4, this is what that code looked like. We create an instance of our helper, because that's how we declare our m, right? Our m is now a field. So how do you declare a field? Well, you don't really, but you create an object to hold it. And so then inside our loop, we're constantly setting that field, and then we're adding our lambdas in, our actions. So later on, when these actions get called, that's going to print out the last value that m had, right? The most recent value, because it's not closing over the value. So in C#5, that moves inside the loop. Every item in our list of things now gets its own helper class, or its own instance anyway, and everything works. So the way this manifested in C#4 was everybody went gung-ho with LINQ. They said, yes, give me a list of all my customers. And then they looped through their customer, and they said, give me a list of all their orders. And then every customer had the orders from the last customer in the list. And it got to be that I remember sitting at where I was working at the time, we had this custom ORM and we had a link thing and we succumbed to this and fixed it. And then we were like looking on Stack Overflow and you could just start reading the first 2 sentences and go, oh yeah, I know the answer to this one. That's this problem. And it generated enough noise that they fixed it. This is a breaking change in the compiler, which doesn't happen much. Probably didn't break anyone, maybe. But anyway, before we finish on closures though, just to complete the story, if we close over something from outside the method our lambda is in, things get a bit more tricky. So we can't just hoist Z up here to be a field on our class, because Z is now living in our outer scope. It could be set by another method on this class. It could be a public thing that gets set by who knows what. It could be a property or a method that does some work. So this now has to capture the entire class. So it's actually capturing the this. If you think about it, if this had said this.z, it kind of makes a bit more sense, right? Z's like an implementation detail of what we're pulling off the class. It has to close over the whole class. So the reason I mention this is back to knowing about performance characteristics. Earlier I said that to avoid potential memory problems, it defines the smallest class it can so it doesn't hold your class in memory. But if you do this, you're now forcing the compiler to basically do the thing that it tried to avoid doing. So good to know. All right, last thing on for each loops is yield, because yields are fun. Because yields, when you look at them, they look like magic. And then when you peel the curtain back, they really don't anymore, and it's kind of disappointing, because you never get that moment back. But this is an iterator method, or getInts is an iterator method. So if you haven't used one, what will happen in C# conceptually is we call getInts, we get back a 1, and we do some work, in this case console.writeLine, and then somehow we call getInts again, but we skip over the 1 and somehow get to line 2 of that method and run that code, which seems really weird. So how does it work? Here is our while loop. I've simplified it down just using a using statement. And here's our iterator method. So there's another helper, getInts helper. In fact, I'll show you later. So we have another helper class, much like with our lambdas, and we're passing in -2. Okay. The interesting thing here to note, and this is true of all for each loops, getInts is only called once. Right? We call getInts, we immediately call getEnumerator. It's the enumerator that's important, it's the numerator that we're going to deal with. getInts itself is only called once. So, I don't know, maybe that's a clue if you're really smart. Not for me. Anyway, let's look at our helper. Our helper implements every interface, because it should, I guess, to be thorough. And it has a few fields. It has a state field, which kind of spoils the fun, gives the game away. It has a current, because it's an enumerator, it has a value. Has an initial thread ID, because we're going to do some threading, although not much, it's okay. It has to implement some things from an interface, that's fine. It has a constructor, which gets the initial state, which was -2, very good. And it captures the current thread. Has a dispose method, which doesn't do anything, and it has a reset method, which doesn't do anything, because nobody ever calls reset. And then it has a getEnumerator method, which starts to get a bit, ooh. I'm sorry, I've just like thrown all this code at you. But at least there's not many generics. So getEnumerator, let's just talk through it. So if our state is -2, which it is, and we're still on the same thread, set state to 0 and return ourselves. Otherwise, if any of those conditions aren't met, create a new instance of ourselves, or of this type, and return that. So this is another one of those little optimizations where, in the best case, the compiler is trying to write code that will do the best thing. So if you have an iterator method and you call it and loop through it on the same thread and only ever do it once, or only ever, then you'll just use one instance of this helper. But if that's not true, in order to not mix up your iterators, I was pointing at 3, now I'm at 7, we create multiple instances. So again, performance, it's good to know. As soon as you use an iterator method, you could get lots of instances of these helpers created. 1 per thread, or just 1 per time it's used in your method. And then we have our movenext method, and if you didn't work it out from the state field, this is a state machine. So the way you split up that method to do line 1, then line 2, then line 3 is you rewrite it into a switch statement that has case, then this case, and then this case. So movenext is the method that's called lots and lots of times, right? That's the one that we loop through. So every time movenext is called, another chunk of our method is executed, and we set state to point to the next one. It's kind of like disappointingly simple, because yield looks so magical. And obviously this gets a bit messier when there's other code in the mix, but essentially all of the other code goes in the middle here. The state variable, the state field, it transitions a lot. So -1 means that it's fetching the next value, which in this case is just a 1. And then the state represents the thing. And then there's -3 states you'll see, there's all sorts of things. But so this is, essentially, it's just a state machine. What other state machines are in C# that have movenext methods? Async await. So once you know how yield works, because you can write a very simple example with yield, you might feel brave enough to then go on to async await. But you have to be very brave, because it's very messy. But essentially, this is very similar to yield, right? We're going to run some code. Now we're going to wait for something to happen. In the yield case, we knew what it was. We were going to go back here and do some whatever it said. We don't really know what's going to happen in this. But essentially, do some code, something. We stop executing this method, and then we want to come back in. And if you've ever seen an exception from an async method, the word movenext appears a lot. And now you know why. I'm kind of guessing that at some point someone just copied the code for an iterator and then just started working. That's how I would have done it. And so our movenext method, and I'm not showing async await because that's like could be an entire talk, but our movenext method is not dissimilar. We have a state. We come in, we execute our first bit of our code. Then, well, we're going to await a task delay, so we get an awaiter. Again, as an optimization, it checks, have we already finished? Right? On a task.delay, probably not, but you never know. Sometimes tasks can finish quickly and before anything happens. But if we haven't finished, we set our state variable ready for the next one. We go off and do whatever magic it happens to stop this and wait here and hook up callbacks. But then essentially at some point, we'll come back into movenext. Our state's now 0. We execute our second chunk of code, and we do the getAwaiter. Now the state bit is interesting because if you ever have to debug an async method, like with tools like WinDBG, or Visual Studio can show you this stuff, the state field is where you are up to in this method, counted by the number of await keywords starting from the top of your method going to the bottom. And so it can actually really help you, like if this throws an exception from, after write line 3, your exception's not coming from my async method, it's going to come from movenext. It's going to come from this whole other class. But so if you can find out the state field and what the value is, you just go and look at, oh, right, we're up to there. So let's bring it all together. Kind of. I cheated a bit. There's some more in this. If you weren't convinced yet why this is interesting to know, this is some completely arbitrary and silly code, but it doesn't do much. It's not very exciting. It's got a couple of loops. It's about 10 lines of code. If you looked at this code and perhaps your manager looked at this code and said, this is too slow, or this uses too much memory, or whatever, improve the performance of this code. At first glance, this code has 1 loop, 2 loops. That's kind of it. It has an order by, like you could find a faster sort algorithm maybe. It's kind of hiding all of its complexity. But if we know what the compiler does, well, okay, this loop, that's just going to be a while loop. That's fairly safe, fairly standard. We have an iterator method though, so that's going to get a helper class created. We're going to have an instance of that. We might have 1 instance per thread if this is some high-load threaded console.writeline app. That could be a problem. Inside that helper, well, we're going to have a state machine that returns a 1. That's easy. But it also has a yield return inside another loop, which I didn't cover, but essentially that means that inside that helper class that is an enumerator, it stores another enumerator, which is the one for the inner loop. More importantly, that helper class uses this.min, so it's going to keep a reference to that whole class that this is all sitting in. It also uses max, which is going to get hoisted to a field. That's fine. No, it's not. Sorry. It's not. Now it is, because it has a lambda, right? So we're going to get a helper class for our lambda that's going to live on our helper class for our iterator. They're both going to capture the class that this resides on. One of those things could exist per thread, and that's the one that has the other, right? So you can sort of start to see that all this complexity, whatever, can creep into your code. Now, that's not to say you shouldn't use these features, because they're fantastic, right? This is the reason to write C# and not just write IL and goto statements, is because it has these high-level functions. But if you're aware of what's going on, when there comes to be a problem, hopefully you can make some more interesting choices. So you've done it. Thank you. Well done. You survived all the code I was going to show you, or at least the PowerPoint code. But where to next? Because hopefully, maybe, you're interested in this stuff now, or were before, and that's why you came here probably. So there's a few recommended things that I would say. If you're brave, the Roslyn compiler is awesome. And actually, you don't even have to be that brave. Let me zoom across here. So this is Roslyn. This is the C# compiler. And if we look in the Microsoft Code Analysis C#, there's a folder here called lowering. And it's not very exciting. It has about 8 files in it. And it has a folder for, hey, iterators, we talked about them, and lambdas, we talked about them. And these are all called rewriters, because what happens is, right, none of this stuff actually rewrites your C#. That was a complete lie. But the compiler parses your C# into a syntax tree, and the rewriters rewrite the nodes of that tree. So some of them are reasonably complex, like async, iterators, and lambdas. They do a bunch of work, so they've got their own folders with classes and things. But there's this folder here called local rewriter. And it has lots and lots and lots of files, because lowering is used in lots and lots of places. My favorite, or not my favorite, but one of my favorites is if. The if rewriter I like, because I always think of if statements as being extremely simple. And I said that IL could do branching, which is basically an if statement, so why does it need to be rewritten? So the cool thing about Roslyn is the comments in this bit are awesome. They pretty much, for every one of these, there is a comment that says this code becomes, and it shows you what the output's going to be. And it shows you in this pseudo, not really IL, but also not really C# thing. But you can see, so if condition, run some code. Well, as I said, if at the very start, IL doesn't have blocks. We can't say run this bit of code. So what we have to do is flip the condition and say, if we're not running, skip that bit of code, right? So back to branching. If we look at foreach, there's actually 4 different lowerings in here. And this file also got slightly more complicated since I did the slides, because now it's async enumerable as well, but there's not a big difference there. But so you can see, this is essentially what I had on the slides, right? Here's our 2 casts, V and T, because, I don't know, they always use single letters, I never know what they mean. But if we scroll down, like even the bits, so this is the bit responsible for 2 lines. Like as you read this, you kind of can get used to it eventually. It's a bit weird. Where are we? I'm just going to keep scrolling. No, we're still in the first one. Nope. Here we are. So this is a special case for foreach, which for any collection that has indexing. So you know how I said foreach lowers to while? Well, it turns out I'm just full of lies. It also lowers to for if we have indexing, right? So there's 4 different special, well, there's one general case, I guess, and 4 different special cases. This uses IEnumerable even less. There's one for, I think it's arrays and then strings. I can't remember. No. Lower for each, a single dimensional array. And there's one more. Multi-directional array. I don't know why I said strings. Anyway, so yeah, Roslyn is the source of truth for this stuff. But it can be hard to read, especially, here. This expression is this, which is like 6 characters out to 8 lines, and some of the rewriters are not written so verbosely as this, and they're just like, here's a new node, and it's all backwards because you have to pass in the things inside you, so it's all you got to read it backwards, so it's a bit weird. So Roslyn can be confronting. Your favorite decompiler is an option, and well, that's true. SharpLab is my favorite decompiler. although it's not technically a decompiler. So SharpLab, if you haven't used it, and if my, oh, come on. This could mean the Wi-Fi is not working. Hey, it worked. So this is SharpLab, sharplab.io. It's a lovely open source free thing written by a lovely man in New Zealand. And what it does is you type in code on the left, which that's the example from my slide, and it will compile your code. And by default, it uses the latest C# compiler, but you can select whichever compiler you want, including these C# next things. These are actual feature branches from the Roslyn GitHub repository. So you can test out function pointers to your heart's content. I don't even know if they'll ever make it in C#, but you can still compile them. But then what it does, well, in one of its modes, because it has a bunch of different modes here as well, but what it does is, so it's compiled this code in C#8, and then what it does is it says to ilspy, which is what it uses to decompile, it says, hey, can you decompile this code, please? I wrote it in C#1. So all of the features that have been added to C#8, ilspy doesn't get to use. And then it also turns off a bunch of other things so that ilspy doesn't use any of them. So this is, you know, it's kind of as close to raw representation as you can get. It's, as John says, you shouldn't trust it. It's not real, but then none of this is real because lowering doesn't actually happen to C#. It happens to bound nodes on a tree. But we don't read bound nodes. Although actually, I think that is one of the options here. Yeah, syntax tree. But so this is where our 8-line for each loop that doesn't do much turns out to actually do quite a lot of things. Look, see, I told you, no one ever calls reset. But yeah, so here's our get enumerator. Here's our state machine. Here's where we're at. See, I said there was another enumerator inside the state machine. That's S2 for those playing at home. Here's our actual code. Here's our rewritten getInt method, which creates a helper. So SharpLab is awesome for looking at this sort of thing, and it shows you everything. I think I've got to go back a bit more. Yeah, the async one, just to, if anyone really wanted me to show async, well, I'm not going to because it's horrible.
Can you toggle it from debug to release and make the difference?
Oh, that's a good idea. So, well, yeah.
The difference is creating a struct instead of class.
Oh, right, sorry, yes. Yeah, so the async case is particularly, I won't say confusing, but it's a lot harder to read because if you look, so we have our statements here. We have gotos inside all these cases, but then they all flow through to this one, which then jumps around within itself. So, yeah, but basically, it's we come in, we do some work, we're going to await, but if we've already completed, then we want to just continue rather than wait to be called back again. Is kind of why it jumps around. But this gets, messy. It doesn't help that all these things have silly names, but you kind of got to extract them out and then type the names in. But yeah, so SharpLab is like, I love SharpLab. It can also run your code. It can show IL. It can do a bunch of things. Wrong way. I told you I hadn't used this before. Yeah, so SharpLab. I think that, yes, that's all. Yes, there you go. Thank you. SharpLab is awesome. I've ruined it for myself there. But what I was going to say was the performance thing is the reason to understand this, and hopefully maybe some of you are just interested. But I find myself forever just, and if I'm writing some code, don't know what it is, but there's just like, at least once a week, I will be curious about, is this the best way to do this, or should I do something else? And I'll go to SharpLab and I'll find out. And it goes along with reading the code of the .NET framework, since we now can do that there and see, is this method implemented better or whatever. And it just helps you hopefully prevent problems, but also understand them. And then, if anyone has any questions, feel free, or I will hang around.